CEO of FCT Combustion at its European headquarters in Vienna, in Austria. So Joel, we can see you and we can hear you, and your PowerPoint is in the right format. So please do go ahead and give us your presentation. Thank you very much.
All right, thank you very much for the introduction, Rob. So today the target is to talk about a little bit about how to produce calcined clay. It's a very hot topic at the moment. Let's start. A little bit about FCT, just a couple of slides. I don't want to spend time on this. FCT basically is an Australian company. So our headquarters is in Adelaide, in Australia, and we have different offices in different parts of the world. Our main offices are in Australia as our headquarters, here in Austria, and in Florida, in US. And then we have other satellite offices like in Brazil, Turkey, and smaller ones with partial capabilities, or we have agents also distributed all around the world. So the company was founded in 1985, and our main markets are cement, lime, different minerals, steel, and so on. The company itself is divided in three main branches. One branch is making FCT flames, is making special flame effects for Olympic Games, for example. A second part of the company is making analytic equipment, XRD, XRF measuring devices, online or offline. And the third part of the company that we will talk today is FCT Combustion. That is, we are dealing with everything related to combustion in heavy and energy-intensive industries. FCT started as a burner designer in the past, but now our range of operations has increased a lot in the last decade. And when we look to, for example, to a cement plant, we are experts in our team that can participate in projects from the beginning, from the quarry to the end, to the end product in a cement plant. So, all right, now coming then to the topic of the presentation. So we all know that CO2 emissions is a topic in the world. The CO2 emissions have been increasing drastically in the last decades. And when we look to the CO2 emissions, we see that a huge part, so we can see here in gray, a huge part, or 50% approximately, is coming from industrial sources. And when we take a look of this, the cement production itself is responsible for around, this number varies a little bit, some people say 5, some people say 10, but it's around 80% of all man-made CO2 emissions in the world, around 80% are coming from cement production. And obviously, more and more the countries are adopting strict policies, especially because of the international agreements put in place and so on. So there are different ways in a cement production how to reduce CO2 emissions. I think in this conference, some of these ways were already discussed in terms of alternative fuels. So as I mentioned, FCT has a very good reputation in terms of alternative fuels firing. We have a lot of innovations in this area. For example, we have a special distribution for axial air that improves the mixing of the fuels with the secondary air. We have a different distribution of SREO air that improves ignition and NOx emissions. We have a special air injection in the end of the alternative fuel pipes to improve, again, mixing and combustion of alternative fuels of different types. We have mostly the diameter of our burners, they are compact, so what improves again the aerodynamics in the kiln, and all this together allows us to make a very short and intense flame with different types of alternative fuels. So, but this is just to touch here that one of the ways to reduce the CO2 emissions is to use alternative fuels. And this, we have a very long expertise on the topic, but the topic of today is not directly on the combustion side, but on the material side. So Basically, we all know that cement, we need to take calcium carbonate and remove the CO2 from it. You can, obviously, there are some researches and some already industrial installations that can recover the CO2 emitted by the calcium carbonate. But another way to prevent, so this would be to recapture the CO2. But before you can emit the CO2, you can prevent it to come to the process. So one way would be to replace clinker, that is a very intense, that produces a large amount of CO2. So we can replace the clinker by other different materials called supplementary cementitious materials. And these materials are basically, we all know part of them. So for example, fly ashes or metakaolin or slag. And these materials, basically, they are amorphous materials and they have hydraulic binding characteristics, similar to clinker. There are two different types. There are natural types and man-made types. And what we use normally is, here you can see in the picture some examples. And one alternative way to do this is to produce the calcined clay or synthetic pozzolan, as we call it. There's a lot of information in the presentation that I believe you receive a copy, so you can go through this information and see more in details. But because of the limited time that we have, I will go through quickly through some points. And in case of doubts later, you can contact us and ask some questions. So my contact details are at the end of the presentation. So feel free to pop up some questions or some email. But basically, what we want to say is that when we are producing, when we compare the CO2 produced per kilo of cement, comparing a normal ordinary Portland cement and a cement with 40% pozzolan, 40% calcined clay, it depends on several numbers on the performance of the plant and so on. But just to have an idea, we can have a reduction of 30% of CO2 emissions coming from the material, comparing the cement with 40% pozzolan to the ordinary Portland cement. And also, because of the specific consumption to produce the calcined clay is much lower, we also save CO2 from the fuel side. Luckily for us, the clays are available all around the world. There are different forms of clays. The clay is normally heterogeneous, so you have a mix of different types of clays, but they are all present all around the world. The main point of the clay calcination is that to calcine the clay, so the clay would be aluminosilicose oxide, and you need, basically what you need to do is you need to heat the clay up to a point where the OH, the hydroxyl, is leaving this material, right? And we can see this very easily in a test called thermogravimetric test or a differential scanning calorimeter test. Basically, what we do is we take a sample of the clay and we start heating the clay. So here at the bottom, you can see the temperature. So we start from ambient temperature and we start increasing it. And you can see, and you measure the mass of the sample during the test. And you can see that during the first around 100 degrees here, you have a decreasing mass. So this is the evaporation of the moisture that you have in the clay. Later on, you have, when you continue increasing the temperature of this material, you have another very important reduction in mass, and this is exactly the range of temperatures in which you activate your clay, where you are releasing the hydroxyl from the clay. And if you continue heating this particle, you can see a third change in mass, and this would be then a change in mass followed by energy exothermic reaction, and this would be again the recrystallization of the clay structure. So these three temperatures, so obviously the moisture evaporation is always here at 100 degrees, but the other two temperatures for clay activation and recrystallization of the clay depend on each type of clay that you have. Obviously, you should reheat the clay, passing the point in where it is completely activated, but not coming to the point of recrystallization. Because you want to keep the clay amorphous, in an amorphous form, because this is the most reactive type of structure. Basically, there are, I just show here some examples. There are three main types of clay: kaolinite, illite, and montmorillonite. They have different layer structures, and they have different crystal activation and crystallization temperatures. Basically, we can see this better in the next figure, in the next chart here. This is an example of kaolinite. So we can see here in the red box would be the activation temperature. Here on the right side would be the recrystallization temperature, and we can see that kaolinite is being activated between around 450 degrees to 600 degrees, and the recrystallization occurs then starting around 900 degrees. So this is a very easy type of clay to use, because there's a very large difference in temperatures between the activation and the recrystallization of the clay. So you have a very large margin of error. Let's say you can have a very looser control of the process, so that your temperatures are coming perhaps a little bit higher in the 700 degrees. Obviously, you spend more fuel, you spend more energy, but you don't cause problems to the reactivity of the clay. From the other two types that we showed before, we have illite. You can see that the temperature range for activation is a bit longer and closer to the reactivation, to the recrystallization zone. And montmorillonite is the most difficult of these three to use, to activate, because the end of the activation and the beginning of the recrystallization are very close together. So you need here a very good and tight temperature control in your process. So basically, there are three main topics that you have to take care. One would be the optimum calcination temperature, how is the crystallinity of your clay, and the mineralogical composition of your clay. One important point that has to be taken in consideration is the color control. The color of the clay has nothing to do with the cement resistance, but has an influence, a psychological influence on buyers. So basically, there is iron in the clay, and iron can be in different forms. When it's in the form of hematite, it has the brown red color, and when it's in the form of magnetite, it has the dark gray color like clinker. So mostly in temperatures higher than 650 degrees, we have most of the iron is in the magnetite form. And the main topic is to activate the clay, you are going above these temperatures. The main topic is when you are cooling again the clay, that you keep the iron in the magnetite form. So there are different ways to do this. One would be to control the atmosphere, so the oxygen content, and another one would be through a chemical control using inorganic modifiers. And you want to make this cooling somehow fast, that the minimum amount of magnetite converts back to hematite. To produce calcined clay, you have different technologies. The two main technologies are a flash calciner or a rotary kiln. FCT is able to offer both of these options. And now I just want to go quickly through the main characteristics of both of them, that you can have an overview. So the flash calciner is basically a preheating tower of a cement plant with a calciner on it. So it's a pre-calcining tower, much smaller size, but the idea is the same. So you have some some cyclones on top of it that are preheating the material. Then you pass this preheated material through a calciner, in which you are controlling the temperature. You are controlling the temperature of the process, similarly to what is done in a calciner of a clinker kiln. And then in the bottom of this tower, you have other cyclones to make a cooling of the product, or a different type of cooling depending on color control and so on. But the main characteristics of this type of equipment is that you have a very low amount of refractory. So refractory you have basically only in this calcining part, and this gives a very fast heat up of the system. So you can start heating the system and producing a couple of hours later on. You don't have virtually no moving parts. This means, except for fans, you have no moving parts, so a very robust and low maintenance light structure, very reliable. And as you know from the clinker kiln, you have a very precise temperature control. So you have to feed to this tower the clay already in a fine form. Most of the clays in nature are already in a fine form. They are just agglomerated because of the moisture. So you have to feed here. In some cases, you need to have a dryer prior to it. In some cases, you need to have a dryer and a mill. Depends again on the type of clay that you have. But you have a very good temperature control. As said, you can dry the material before in different ways, and perhaps you need also to grind it, but most of the clays are already in a fine form when dried. So most of the cases, just a dryer is enough. And to supply energy, thermal energy to this process, we need hot gases to activate the clay. So one option, again, speaking about CO2 reduction, is to have a hot gas generator, similar to this one in the picture, that can burn different types of alternative fuels. We, as FCT, we have standard units that are already designed, and we can also design larger or smaller, depending on client needs. But these are the four sizes that we have in standard. And we have pilot plants also in Europe and South America that we can use for different types of tests. The second technology would be the rotary kiln. We are also offering that. We can both make a revamping of an existing kiln, a clinker kiln, and convert it to pozzolan production, or we can make use a kiln that has a double function. In some months of the year is producing pozzolan, in some months of the year is producing clinker. But basically, there's nothing much to say here. Is a rotary clinker kiln. There are some differences in the feeding to the kiln. So we would not use the pre-calciner or the preheater of the kiln. We would feed the clay directly into the kiln, and this gives us a bit of freedom in terms of how the clay is prepared. So the clay can be much higher moisture, can be in larger lumps, and so on. This also allows us to use decommissioned kilns. Some plants that have kilns that are stopped for some years can be reused for that purpose. And this brings down obviously the initial investment, and also can accelerate some projects developed to produce calcined clay. Again, in terms of alternative fuels, it's a little bit more tricky to use alternative fuels in the rotary kilns, but it's also possible. What is very important to say is that there are these two technologies, the flash calciner or rotary kiln, and it's impossible to give one answer that fits to all purposes. So it depends a lot on how much moisture you have, what is the mineralogy of your clay, the fineness of the clay after it's dried, and so on. And each case has to be studied differently. We just want to say here some advantages of each process. So when we are speaking about flash calciner, because of the very good control of temperature that we have, so the particles are very fine, and you can have a the temperature be controlled in a very narrow range. So in general terms, you can have a higher reactivity of the clay simply because you can control better the temperature. So you don't need to calcine to grind the final product, but you grind the product, the raw material. You can start very easily because of the low quantity of refractories, so you don't need to heat the system for such a long time as a rotary kiln. You have a lower fuel consumption, maintenance costs are lower. The overall electrical consumption, when you consider the whole process from the beginning to the end, including grinding and so on, is also lower. And if you have to buy a new equipment, in general terms, the return of investment is faster in a flash calciner than if you buy a complete new kiln. Obviously, the rotary kiln has also its advantages, so it's more forgiving in terms of, it's less sensitive in terms of which type of raw material that you can use. As I mentioned, you can use larger moisture, you can use larger particle sizes, and so on. So the secondary air temperatures are much lower than in a clinker kiln, so it's harder for you to use higher amounts of alternative fuel, while in the flash calciner, you produce the gases in a separate hot gas generator, and there you can control much better the combustion. You don't need to grind the raw material, but you grind later on the fine material to put to the cement. And the main advantage of rotary kilns is that in most plants, there's a rotary kiln that is stopped and can be repurposed for calcined clay production. In our website, you can take a look, fctcombustion.com, clay calcining technologies. You can see a diagram that we developed as a roadmap to help you to understand which type of equipment you would need for depending on the type of your clay. Obviously, we can make this study together if you give us some more information about the clay that you have available. But here is just to give you a first idea which type of equipment is more suitable for you, the rotary kiln or the flash calciner, depending on moisture. If you have, for example, a clay with a high moisture above 30%, you would need a pre-drying, different types of pre-dryer. If you have a coarse material, you can go directly to the rotary kiln, for example, or you can grind it and grind and dry it, depending on then how much moisture you have and so on. So if you follow the diagram, you can see which type of equipment you need before the flash the calcination unit, and then which type of the calcination unit is more recommended to you. Likewise, depending on your fuel source, if it's a gas, a liquid, or a solid fuel, and also depending if it's a pulverized fuel, like a pulverized coal or a coarse material, different technologies for hot gas generation. Or if you have in a rotary kiln, you would use directly the burners directly in the kiln. And a third point here, depending on how much iron you have, if you would require some kind of color control or not. And obviously there are some other considerations that have to be taken in consideration in each case. CapEx, which equipment are available, which footprint are available on your plant, how is the raw material quality, characteristics, and so on, their handling of raw material, and so on. And obviously, as I said, this is just a general diagram to help, but we can be contacted in a case-by-case scenario that we can check which solution is better for your specific case. When we are talking about a project, a calcined clay project, and we are coming already to the end of the presentation, when we are speaking about a calcined clay project, is the most important part is at the beginning, because at the beginning you should make a very good characterization of the clay, because this will dictate all the other steps. So this will dictate which type of calciner is better for you, the rotary kiln or the flash calciner, which kind of additional equipment do you need, in terms of grinder, in terms of dryer, which kind of fuel you want to use, which kind of gas treatment you need to have after this unit, and so on and so on. So if you want to have, for example, a high amount of alternative fuel as a fuel source, then perhaps you need to think also again about desulfurization unit for the gases, or a chlorine bypass, and so on. And just a little bit about our experience with calcined clay. So our team was involved already in 12 projects like this in the whole world. Our guys, a lot of our guys are coming from cement plants, and in Brazil, specifically South America, in Brazil, the use of calcined clays is already coming from a long time. From the 80s, were the first kiln producing calcined clays, and since then, our guys have experience with that. We are able to help you since the beginning, from the quality tests to be made in the clays that you have available, and some process tests. We can make laboratory tests and also industrial size tests. And at the end, we can make the complete process from the beginning, from the quarry you can deliver the complete process from the quarry to the end product in one company. No? Basically, to end the presentation, I think we are a little bit over time. There are different solutions to process clay, to calcine the clay, to activate the clay, and each solution has a trade-off. So depending on each specific plant, on each specific product, you should go in one direction or another, and we are ready to support our customers to choose the most appropriate method and which equipment is necessary for each case. This was it from my side. I think the main message here is that there are different ways to avoid CO2. So CO2 production, one would be not producing it at all. One would be to reduce its production in terms of fuels. Another one would be to recapture the CO2 at the end of the process, but a third one is to not produce it at all, and this is possible with using calcined clays. There are different possibilities in different parts of the world. There are legislations how much calcined clay you can use, but what we can see is that more and more the standards are being upgraded to allow more calcined clay. That's it from my side. You have here my contact in case you have some questions in the future, and now I'm open for questions for the moment. Thank you very much.
Thank you very much indeed, Joel. Very, very interesting presentation. This is actually the first presentation that I've seen on calcination of clays going into this depth. So really, really interesting. Thank you very much indeed. I just have a very, very quick question to start off with, and that is, you suggested that in the flash calciner, that you would only apply refractory to essentially the lower half of the reaction vessel, and that the rest of the system would actually be not, if you like, insulated. But then a little bit later, you showed us another photograph, which apparently had a flash calciner with thermal insulation blankets applied to the outside. Is that correct?
Yeah. So yes, correct. So what I meant is that in terms of refractory material, that is the heavy part and the part that you have to heat for a long time period, this is only in the inner part of the calciner, right? The other parts of the tower are not internally refracted, but what we normally use is just insulation outside to reduce. So we are talking about lower temperatures, much lower temperatures, but it's to reduce thermal losses to the process, to improve the efficiency of the plant, and also for safety, for reduce the temperature to touch. No? That's all. And okay. This insulation outside has a much faster heat up time. No?
For sure, for sure. So we have another question that's coming from Asep Udi, who says, What is the pozzolanic reactivity index for activated clay in ASTM test?
It depends. There are different. There is no answer that fits to all. Depending on the type of clay that you have, depending on how much alumina or silica you have, how much this alumina and silica are combined together, how they are combined together. So this will dictate you also the temperatures that you are using. This will dictate you the reactivity index. So there's a test that you can make with the clay, and this test will tell you how much would be the reactivity index of your clay. So I cannot answer this generically, so the best is to do a test on the clay that you intend to use.
Right, okay. Because I would imagine that the vast majority of listeners and the vast majority of cement producers around the world are not going to have a pure kaolinite clay, not going to have a pure illite clay, not going to have a pure montmorillonite clay. It's going to be a mix. Even a kaolinite is going to have some proportion of the other ones. So you said, in fact, that in the presence of montmorillonite, you have to have a very specific temperature. I think it was about 820, was it? Something like that?
Yeah.
So you have to calcine those clays at. So how easy is it to get precisely that temperature in either the flash calciner or the rotary kiln?
Yeah, so you have to imagine that in the flash calciner is very easy. It's like you are controlling a calciner of a clinker kiln, right? So you have a temperature measurement at the outlet of the calciner, and you control how much fuel you are using, and depending on this temperature. So it's very easy. The material that it's going through the calciner is very fine, so it's a fineness similar to a raw mill from a clinker production. So you can control the temperature very, very well. In a rotary kiln, it's a little bit more difficult to control the temperature because we have larger particles. So the surface of the particle and the inner side of the particle are in different temperatures. We also have a bed that is revolving in the kiln. So one side of the bed has one temperature, the other side of the bed has another temperature. So from this point of view, it's a little bit more difficult to control, but it's also possible to use a rotary kiln. Even if the clay is a little bit more difficult to be handled in terms of temperatures, it is both technologies can be used, but if you are talking about a very precise control of temperatures, then the flash calciner is better.
Right, and presumably the relative proportions of each type of clay defines at what temperature you will attempt to calcine them at, because actually if you have only 5% montmorillonite, it doesn't really matter whether or not it's 70% crystallized, because actually it's only a very, very minor portion of your calcined clay product.
Correct. So that's the point. So the clays are heterogeneous material by its nature. So the best is to make a test with the specific clay that you have. This test that you have a sample that you heat over time, and then there you can have the answers that you need. No? So there you can see where you are losing the mass from moisture, and then the mass from the hydroxyl, and then where you are recrystallizing again the sample. So this test is a very important test that has to be made in the beginning of the process. A second test to be made later would be, as the other question mentioned, the reactivity index, to see how this would fit to your cement. But this test should be made in the beginning of when you start thinking about calcining clay. Before you buy any equipment, this should be the first thing to be done.
Okay. So I've put your FCT selection diagram in the handouts tab, so people can download that to see if they should start calcining clays, and if they decide to, what process that they should use. Michael Supana asks, what's the influence of RDF on the quality of calcined clay clinker? We only have a very small amount of time, so if you wouldn't mind answering that briefly. What's the influence of RDF? Yeah,
so basically it depends on the technology that you're using, calcined clay, flash calciner, or rotary kiln, but to the quality of the clay there is not much influence. What can have influence is in terms of the gases that you are producing, because as we all know, the